Hello and welcome. So, you're gearing up for your IGCSE or O Level Physics exams, huh? Well, if you really want to crush those super tricky density questions, you have come to exactly the right place. Think of this as your secret weapon for revision, designed to help you master the toughest problems they could possibly throw at you.
Okay, let's just jump right in. I've handpicked 3 classic, really challenging density problems, the kind that often trip students up. We're going to break them down, solve them together, and make sure you walk away understanding the core ideas behind each one. So, you ready for the challenge?
But hang on, before we tackle those big questions, let's do a super quick recap of the basics. Having a solid foundation is everything, and it's going to make the next steps a whole lot clearer.
So, what even is density? Well, put simply, it's how much stuff, that's mass, is packed into a certain amount of space, or volume. A good way to think about it is how compact something is. A block of lead is way more compact, way denser than a block of wood of the exact same size.
And here it is, the magic formula you absolutely need to know. Rho equals mass over volume. That little Greek letter, rho, stands for density, m is for mass, and v is for volume. I promise you, every single calculation we do today is going to come right back to this simple but powerful equation.
All right, recap over. Let's get to our first challenge. This one is all about composite objects, which is just a fancy way of saying what happens when you take 2 different materials, join them together, and need to find their new average density. So here's the problem. We've got an aluminum block and an iron block, and we know the mass and volume for each one. They're stuck together. Your mission is to find the average density of this new combined thing. Now be careful. The big trap here is to just average the densities of aluminum and iron. Don't do that. Think back to that core formula. Go on, pause this explainer, grab a piece of paper, and give it a shot yourself.
Okay, welcome back. How did it go? The secret to solving this isn't averaging the 2 densities. Nope, the real path is much more direct. First, we find the total mass. Second, find the total volume. And third, we just plug those total values back into our main formula. Simple as that.
Now take a look at the table here. It lays everything out perfectly. For step 1, finding the total mass, we just add them up. 270 grams of aluminum plus 1,574 grams of iron gives us a grand total of 1,844 grams. And for step 2, we do the exact same thing for volume. 100 plus 200 gives us a total volume of 300 cubic centimeters.
And now for the big finale. We take our total mass, 1,844 grams, and divide it by our total volume, 300 cubic centimeters, and that gives us our final answer, an average density of 6.15 grams per cubic centimeter. So remember the key. It's always total mass divided by total volume.
Great work on that first one. Let's move on to our next challenge and see how these ideas build on each other. We're taking density into the real world now, looking at how a massive object like a submarine can actually control whether it sinks or floats. This is all about buoyancy.
Okay, here's the setup. We have a submarine with a set volume and a known mass when it's empty. The goal is to achieve neutral buoyancy. That means it just hovers in the water, not sinking, not rising. To do this, it sucks seawater into its ballast tanks. Your job is to figure out the volume of water it needs to take in. Go ahead, hit pause and see if you can crack this one.
All right, ready for the solution? I know this problem can look a little complex, but really it just breaks down into 3 logical steps. First, we need to figure out what the submarine's total mass should be to perfectly match the seawater's density. Second, we'll calculate how much extra mass, in the form of water, it needs to add. And finally, we'll convert that mass of water into a volume.
Let's walk through these calculations together. Check out that first row. Our target is neutral buoyancy, which means the sub's average density has to equal the seawater's density. If we rearrange our formula, the target mass is just the density of seawater, 1,025, multiplied by the sub's volume, 2,000. That gives us a target mass of 2,050,000 kilograms. Now, we know the sub already has a mass of 1.5 million kilograms, so a simple subtraction tells us we need to add another 550,000 kilograms of water.
And for the very last step, we just need to convert that mass of water into a volume. We know the density of water is about 1,000 kilograms per cubic meter, so we divide the mass we need by that density. 550,000 divided by 1,000 gives us our final answer. The submarine needs to take in exactly 550 cubic meters of water.
You are doing an awesome job. It's time for our final and maybe the most complex challenge of the day. This one involves a gas, an air bubble, and it explores how its volume, and therefore its density, changes like crazy with pressure and temperature. This is where we bring in the gas laws.
So picture this. A tiny air bubble starts at the bottom of a cold, deep lake. As it rises to the warmer surface, the pressure on it drops and the temperature rises. We know all its starting conditions. Your task is to calculate its new volume when it finally reaches the surface. And here's a huge hint. For any gas law problem, you always have to use Kelvin for the temperature. Okay, hit pause and work this one out.
You back? Okay, let's just visualize what's happening. As you can see here at the bottom of the lake, we've got high pressure squeezing the bubble and a low temperature. As it rises to the surface, the pressure drops way down and the temperature goes up a bit. This just helps us keep all our before and after numbers straight.
Now, to solve a problem where pressure, volume, and temperature are all changing, we need to pull out a special tool, the combined gas law. It looks complicated, but it just says that for a certain amount of gas, the ratio of pressure times volume to temperature always stays the same. Our goal is to just rearrange this thing to solve for V2, the final volume.
The first step is just a little bit of algebra. We need to get V2 all by itself on one side of the equation. And when we do that, we get this new formula. Now for the easy part. It's just a matter of carefully plugging in all the numbers we have from the problem.
And when we punch all those numbers into the calculator, we get our answer, 9.47 cubic centimeters. Now look at that. The bubble has expanded to be almost 5 times its original size just by rising to the surface. That really shows you the power of changing pressure and temperature.
Fantastic job getting through those 3 challenges. Seriously, you've navigated composite objects, buoyancy, and even gas laws. So, let's wrap this up by boiling all that hard work down into the key takeaways you absolutely need to remember for your exam. So here's what you need to burn into your brain. For composite objects, it's always total mass over total volume. For buoyancy, an object will just hover when its average density perfectly matches the density of the fluid it's in. For gases, remember that pressure and temperature have a huge effect on volume, and always use Kelvin. And finally, the golden rule for all of physics: double-check your units before you calculate anything. We've covered a ton of ground today, and you've done an amazing job. So now I've got a question for you. Which of these 3 challenges did you find the trickiest? Was it the composite objects, the submarine, or the bubble? Let me know why in the comments below. Keep practicing these problems, and I promise you, you will master them.